Imagine standing on a beach, watching one of the largest machines humanity has ever built slowly disappear over the horizon. It's longer than 3 football fields, taller than a 15-story building, and when fully loaded, it carries enough crude oil to fuel entire countries for days. Everything about this ship makes sense until it reaches its destination. The oil is pumped ashore. Millions of barrels gone. The cargo tanks are now completely empty. The ship has done its job. So, logically, it should simply turn around and sail home. Instead, the crew does something that sounds almost absurd. They begin pumping thousands of tons of seawater into those empty tanks. Not a little water, enough to fill dozens of Olympic swimming pools. An oil tanker, carrying water. The first time I learned this, I assumed there had to be another explanation. Maybe the ship needed fresh water for the crew. Maybe they were cleaning the tanks. Maybe they were transporting water to another country. Every one of those guesses sounds reasonable. Every one of them is wrong, because that ordinary seawater is doing a job far more important than carrying cargo. Without it, one of the strongest machines ever built becomes surprisingly vulnerable. Not because of storms, not because of giant waves, not because of pirates, but because of something the crew can't even see. And the strangest part is, this invisible danger only appears after the oil is gone. Welcome to HUZAIF Beyond. Today we're uncovering one of the most fascinating engineering secrets hidden inside modern shipping. And by the end of this journey, you'll realize that what looks like a ship carrying water is actually one of the smartest safety systems ever invented. Let's begin with a simple question. If I gave you 2 identical oil tankers, one fully loaded and one completely empty, which one would be safer in the middle of the ocean? Most people choose the empty one. It seems obvious. Less weight means less stress, less fuel, less momentum, less danger. That's exactly what our brains want to believe. But engineers would probably choose the opposite. Because to them, an empty tanker is often the one that deserves the most attention. That sounds impossible. How could removing hundreds of thousands of tons of weight make a ship more vulnerable? The answer begins with something almost nobody thinks about. Ships don't float on still water. They float on moving mountains. From the shore, the ocean can look calm, peaceful, almost motionless. But out in deep water, the surface is constantly rising, falling, twisting, and rolling. Even on days when passengers barely notice movement, the sea never truly stops pushing against the ship. Now imagine balancing a long wooden plank between 2 chairs. Press down on both ends. The middle bends. Now push upward from the center. It bends the opposite way. Keep repeating that over and over. Eventually, the wood begins to weaken. An oil tanker experiences something remarkably similar, except the plank isn't 3 meters long. It's more than 300. And instead of wood, it's made from thousands of tons of high-strength steel. Every passing wave gently lifts one section while another begins to fall. The front rises, the middle sags. Then the opposite happens. Hour after hour, day after day. Crossing an ocean isn't simply moving forward, it's surviving millions of tiny bending cycles. Most people imagine the ocean attacking ships with one gigantic wave. Reality is far less dramatic and far more dangerous, because giant waves are rare. Small waves are endless. Every single one steals an almost invisible amount of the ship's strength. Not enough to notice, not enough to trigger an alarm, just enough that tomorrow's wave matters slightly more than today's. Engineers even have names for these movements. When the bow and stern rise while the middle bends downward, they call it sagging. When the middle rises while both ends dip lower, it's called hogging. To everyone on deck, the ship still feels solid, but across hundreds of meters of steel, the structure is quietly flexing, not because something has gone wrong, because that's exactly what it was designed to do. Steel that refuses to flex breaks. Steel that flexes carefully survives. At least, that's the goal. So, if ships are already designed to bend, why does unloading the cargo suddenly become a problem? You might expect removing all that weight would reduce stress. For a moment, engineers thought the same thing. Then reality proved them wrong. Imagine carrying a heavy backpack during a long hike. At first, it feels exhausting. But after several hours, your body adapts. Your shoulders settle. Your balance changes. Everything works together. Now imagine someone suddenly removes the backpack without warning. You don't fall over. But for a few moments, your posture feels strangely different. Your body has to find a new balance. An oil tanker experiences its own version of that adjustment. Except instead of losing 20 kilograms, it loses hundreds of thousands of tons. Within hours, the enormous weight that once pressed evenly through the hull disappears. The ship rises much higher in the water. More steel is exposed above the surface. The wind suddenly has a larger target to push against. Waves strike different parts of the hull. The center of gravity changes. The way the ship moves begins to change. Everything the engineers carefully predicted while the vessel was loaded is now different. And that's when something fascinating begins to happen. The ocean hasn't become stronger. The steel hasn't become weaker overnight. Yet the ship behaves like an entirely different machine. The empty tanker rides higher, it responds faster. It rolls differently. It pitches differently. Sometimes, those movements become far more violent than when it was carrying millions of barrels of oil. It almost feels backwards. Adding enormous weight can actually make certain motions calmer. Removing that weight can make them worse. That idea completely changed how engineers thought about these ships, because they eventually realized cargo wasn't only being transported, it was also helping stabilize the structure itself. But stability wasn't the only problem. There was another one hidden deep inside the steel. Unlike a dent, or a crack, or a broken weld, this damage couldn't be seen with the naked eye. It didn't happen all at once. It happened one wave at a time. Picture taking a paperclip and bending it back and forth. Once, nothing happens. 10 times, still looks normal. 20, 30. Eventually, without warning, it snaps. Not because the last bend was especially powerful, but because every bend before it quietly accumulated damage. Steel behaves in much the same way. Engineers call it fatigue. The name sounds harmless, almost human, but fatigue has destroyed bridges, aircraft, offshore platforms, and ships. Not through one catastrophic event, through millions of tiny ones. Every time an oil tanker bends with the sea, the steel experiences microscopic stress, far too small for anyone on board to notice. But metal has a memory. It doesn't forget. Every flex, every vibration, every twisting motion leaves behind a tiny record. Individually, they're meaningless. Together, they can decide how long a ship survives. Personally, This was the moment that completely changed how I thought about engineering. We often imagine disasters being caused by one huge mistake, but many of the world's greatest engineering failures don't happen because something suddenly goes wrong. They happen because thousands of perfectly normal events quietly add up over time. And that's exactly what engineers were trying to prevent. They couldn't stop the ocean. They couldn't stop the ship from bending. But perhaps they could change how it bent. Their solution sounded almost ridiculous. If the ship had become too light, make it heavy again. Not with oil, with seawater. Thousands, then tens of thousands. Sometimes well over 100,000 tons of it. At first glance, it seems wasteful. Why burn fuel carrying water that has no value? Why not simply sail home empty? Because the water isn't cargo. It's carefully positioned weight. Engineers don't just fill random tanks. They choose specific ballast tanks throughout the ship to control how the vessel sits in the water. Too much weight forward, and the bow sinks lower than it should. Too much aft, and the stern drags through the sea. Too much on one side, and the ship begins leaning. Ballast isn't simply about making the ship heavier. It's about making it balanced. But here's where the mystery becomes even more interesting. If seawater is only there to improve balance, then why do modern oil tankers invest millions of dollars building completely separate ballast systems? Why spend enormous amounts of money solving a problem that seawater already solved decades ago? Because engineers eventually discovered the water was protecting the ship from one danger, while quietly creating another. And unlike bending steel, this next threat couldn't be seen, couldn't be heard, and under the right conditions could turn an empty oil tanker into something far more dangerous than one carrying millions of barrels of crude oil. The engineers believed they had solved the problem. The ship was stable again. Its enormous steel hull was no longer being punished by every passing wave in quite the same way. The journey home was safer. At least, that's what everyone thought. Because the real danger wasn't outside the ship anymore. It was trapped inside the tanks everyone believed were empty. That sounds impossible. How can an empty tank become dangerous? After all, if every drop of crude oil has already been unloaded, what exactly is left inside? The answer is almost invisible. Imagine pouring honey from a glass jar. No matter how carefully you empty it, a thin coating always clings to the inside. Crude oil behaves the same way. Millions of barrels may be gone, yet an incredibly thin film remains on the steel walls of every cargo tank. And almost immediately, that thin film begins to change. The lightest hydrocarbons slowly evaporate. Liquid becomes vapor. Silently, hour after hour, the tank that looked empty is now filling with something nobody can see. Hydrocarbon gas. By itself, that gas isn't the real problem. Here's the twist. It only becomes deadly when it mixes with just the right amount of oxygen. Too little oxygen, nothing happens. Too much, and it still won't ignite easily. But somewhere in between is a narrow window engineers never want to enter. Because inside that window, a tiny spark can release an astonishing amount of energy. Not a bolt of lightning, not an open flame. Sometimes something as ordinary as static electricity. The same tiny shock you might feel after walking across a carpet. For you, it's forgettable. Inside a cargo tank, it could be catastrophic. This was one of the industry's biggest realizations. The most dangerous moment wasn't always when the tanker was carrying oil. Sometimes it was after the oil had already been delivered. So how do you stop a danger you can't even see? The obvious answer would be ventilation. Fill the tanks with fresh air. Except that would make the situation even worse. Fresh air brings oxygen, and oxygen is exactly what those vapors need. Instead, modern tankers do something brilliantly counterintuitive. Rather than adding more air, they remove it. Special inert gas systems fill the cargo tanks with gas containing very little oxygen. The vapors are still there, but without enough oxygen, they cannot burn. It's a solution that feels almost backwards. Most safety systems add something. This one protects the ship by taking something away. Just when it seemed engineers had finally closed every loophole, another problem quietly appeared. And this time, the threat wasn't fire, it was water itself. The ballast water that protected the ship's stability came with an unwanted passenger: salt. Every voyage left behind tiny amounts of moisture and salt on steel surfaces. Nothing dramatic happened after one trip, or 10, or even 50. But steel doesn't negotiate with chemistry. Given enough time, salt and oxygen always begin writing the same story. Rust, slow, patient, relentless. The very water helping the ship survive rough oceans was also shortening its life from the inside. Engineers faced another impossible choice: protect the ship from structural stress, or protect it from corrosion. For years, there was no perfect answer. Then someone asked a completely different question. What if ballast water never entered the cargo tanks at all? That single question changed everything. Instead of using cargo tanks for ballast, modern oil tankers were built with segregated ballast tanks. Entire compartments dedicated only to seawater. The cargo stayed in its own system. The ballast stayed in another. Simple, elegant, and surprisingly effective. Corrosion dropped, maintenance became easier. But something even bigger happened. The oceans benefited too. Before segregated ballast tanks became standard, ballast water often mixed with traces of crude oil. When that water was discharged, small amounts of oil could return to the sea. One voyage didn't seem important. Thousands of voyages over decades were. The solution designed to protect ships ended up protecting the oceans as well. Most engineering breakthroughs are like that. Solve one problem properly, and you often solve another without expecting it. You might think that's where the story ends. The ships became stronger, safer, cleaner. Mystery solved. Except the ballast water had one final secret. Not oil, not chemicals. Life. Every litre of seawater contains microscopic organisms. Tiny plants, larvae, bacteria, plankton. Creatures so small that millions can exist in water that looks perfectly clear. Now imagine taking on ballast water near one coastline, crossing an entire ocean, then releasing that same water thousands of kilometers away. The ship hasn't just transported water, it's transported an ecosystem. Some of those organisms die, others survive. And if even a few find conditions they like, they can spread rapidly through an environment where nothing evolved to keep them under control. A system designed to make ships safer had accidentally become one of the ways invasive species traveled around the world. Engineers had solved stability, then explosions, then corrosion. Now they were solving biology. Today, modern ballast water treatment systems filter, disinfect, or expose that water to ultraviolet light before it is released. Not because the water is dangerous, but because of the tiny invisible passengers hidden inside it. When we began, The question sounded almost ridiculous. Why would an empty oil tanker carry water? It turns out that was the wrong question. The better question is this: what happens when one of the largest machines on Earth suddenly loses the thing it was built to carry? The answer is an extraordinary chain of engineering decisions. Water restores balance. Special gas systems prevent explosions. Separate tanks fight corrosion. Modern treatment systems protect entire ecosystems. Every solution exists because engineers discovered a problem most people never knew existed. So the next time you stand on a beach, watching a giant tanker disappear beyond the horizon, remember this: that ship isn't simply carrying oil or water. It's carrying decades of hard-earned lessons written by engineers determined to prevent disasters before they ever happen. And perhaps that's the greatest achievement of all. The safest engineering is usually invisible, which is exactly why most of us never notice it's there. Thank you for watching HUZAIF Beyond.